Thanks for having me and for organizing this conference. I'm sorry I could not be there in person, but I hope to make it up the talk. Let me go full screen so that it's a bit easier. Right. So there's a popular view in philosophy of science, and that view relates to the idea of continuity. As a mathematical abstraction, that is extremely helpful when you model a physical system. And it goes back to the classical days. So Leibniz, Nolli, Du Châtelet, they all believed in continuity because they believed that it is not possible to have a physical quantity, for example, jump a value from a starting position and a final position. And the view remains popular till date, but for different reasons. So let me call a collection of all these views as the Continuum Fallacy, which I'm going to debunk in this talk. One of the versions of this fallacy, which assumes that continuity is very important for mathematical representations of the physical world, comes from Søren Pangu, University of Bergen, Norway, where he argues that even if you do find discontinuities, they're only present in the theoretical structure, or for example, in phase transitions, as we understand them, when you're trying to model a droplet and how heat is being transferred across it. And the discontinuity is not really present in the raw data as such. Another version of this fallacy is based on convenience and empirical adequacy. So Jeremy Butterfield here at Cambridge, just retired, he makes the argument that continuity works, and it works in a huge number of cases. And it's as good as a discontinuous model. And so what's the need for adapting any kind of model that involves all these strange discontinuities? So let's go for a continuous representation of the physical world. And finally, this another version of this fallacy, which is based on this idea that it is not only the case that continuity is important as a mathematical tool, it's that we cannot dispense with it. And the reason why we cannot do that is because when we do describe a physical system, we often find that a description that is continuous is often decoupled from a system's microscopic details and all the dynamical laws therein. And therefore, Batterman at Pittsburgh, he argues that these idealizations are emergent. They are not visible right away in the world when you look at the world, but they're right there because they emerge under some limit. And there's another virtue, which is that it allows to explore different parts of physical system that you would not be able to explore if you go for a bottom to top representation that involves all the details from a system's microscopics. And so therefore, they argue that all these models that involve continuity are somehow superior to other kinds of models. So therefore, the catch here is that the mathematical abstraction, the bigger picture, is that the mathematical abstraction called continuity is really important, and might even play a very important role in our understanding of the world. And I'm going to debunk this whole thesis. In a recently published paper, we argue in Foundations of Physics, we argue that when we think of the case of temperature, at least, and so for many different physical quantities and the way they vary in space and time, they are not really continuous functions. They are continuous within certain limits, but once you expand those limits, you find that it really depends on various contingent factors. And in fact, importantly, various microscopic factors, which these continuum models tend to resolve. And they argue that these are not important, but I would argue that they're very important in understanding of what is going on in all these cases. And I'm going to argue that the evidence of discontinuities, for example, in the case of temperature, runs from both the macroscopic part of a physical system to the microscopic details, up to the nanoscale, up to a really, really small length. And this is observed in experiments, in simulations, in theoretical predictions, and in models that study this part of the system. And I'm going to also argue that because of these reasons, continuum models, as we like to believe, they're not decoupled from the microscopic level. It's just that in the cases that Batterman or Butterfield or other people, they describe, they tend to take cases where it just seems to work. And I'm going to argue that this is not always the case. And that is where a lot of important emergent anomalies have been discovered in physics and applied mathematics. And these might give you a better understanding of what's really happening on the ground, which these continuum models might fail to give you. And that raises a deeper question about this whole dichotomy about continuity and what is discontinuous, and are these mathematical things even there? So I'll raise a brief question about that in the talk. The structure of the talk is roughly, I'll discuss two cases, one based on discontinuities across liquid vapor droplets in phase transitions, and another based on solid-solid interfaces in what we call as thermal boundary resistance, where a material resists the flow of heat across a junction. And then I'll put my conclusions out there. So let's go to the first case. Importantly, in many studies of evaporation of a droplet, which is undergoing evaporation in a thermal bath, we have observed significant discontinuities of the order of 25, 23 kelvins. And this discontinuity has been observed at the scale of, from a few micrometers, which is where the collision path of molecules lies. So there's the distance at which molecules collide with each other. And so if you look at this diagram in front of you, so you have this red liquid bulk that is evaporating. And so if you, let's say, zoom in on this droplet, you find that this red bulk has a little interface, which is given by this dotted line. And across this little interface, which is the order of 10 to the power minus 6 meters, there is a huge jump in temperature. There's a transition layer between the liquid and the vapor bulk, which we call as a Knudsen layer. And in between this layer, the temperature could still be modeled as a continuous quantity. But when you take the whole thing from the movement from liquid to vapor, the research shows in the last 30, 40 years in applied physics that even though in most cases it is possible to model the situation as a continuity, it will give you incorrect predictions in many of the cases. And the reason why that is the case is because certain contingent conditions around the droplet, for example, if you change the vapor pressure, if there's a contamination of the surface, and many of the factors that might cause this strange discontinuity. And what's important is that in all the continuum models that we like to study evaporation, they fail to give you a right amount of heat flux across the liquid surface of the droplet. And often the predictions are off by 70, 80%, which is a huge number. And so when applied mathematicians and scientists model this variation in temperature and variation in heat flux across the liquid boundary as a discontinuous quantity based on certain parameters that I'll discuss shortly, then they find that it is often possible to improve the prediction substantially. And they can get really close. And this is important when you think about combustion engines. It's important when you think of evaporation in the atmosphere. Any situation where you have high pressure, we might have a situation where there's something undergoing evaporation at a very high rate, where the usual continuum models tend to break down. So I'll discuss one model, and I'll try to skip the technical details, but still give you a broad overview of exactly why discontinuity is important in the modeling process. So one way of understanding the amount of heat flux that is being transferred from the liquid to the vapor bulk is to read the amount of entropy change that happens across the bulk. In classical models, we assume that temperature is continuous across the interface. But in more recent models that model this discontinuously, we take three components. The first component, as you can see, is delta SC by KB, Boltzmann constant, which is the classical component, which essentially assumes that temperature of the liquid is the dominant temperature across the interface. And so you can see that in this model of delta SC by KB, you only see the TL term, which is the temperature of the liquid term. There's no TV term that appears in this particular term. There are two more terms in this equation that models the total entropy change in the system, and the second term is the change in because of temperature discontinuities. And this factor includes the microscopic dynamics of what is happening in the interface. So it assumes that it is not only the case that liquid molecules are being transferred from the liquid bulk to the vapor bulk, but also that many molecules in the vapor bulk are being retransferred back to the liquid. And that happens because of many different dynamical factors which we don't fully understand yet. So evaporation is a really tricky phenomenon to understand. And I don't think we have a full understanding of it yet based on the dominant literature in applied physics. And so when you look at these other two terms, which include discontinuity and include this dynamics across the interface at the microscopic level, which is happening at the scale of, at the molecular scale, you do see a lot of TVTL terms, which is vapor temperature and liquid temperature terms, which are different, which are assumed to be equal in the classical delta C by kV model. What happens is that the flux or the entropy change based on which the flux is calculated is significantly affected by this discontinuity, which was completely discounted in the continuum model. But what's important to know is that in many of the models, you cannot really derive discontinuity. So there's no mathematical framework that lets you discover suddenly that you'll find some kind of discontinuity. So this is taken as a starting point of the model that models the entropy change across the interface. And the reason why it's taken as a starting point is because it's based on many theoretical predictions, based on kinetic theory of gases, based on Boltzmann transport equations. It's also based on experimental data, like the one that I showed you in the last slide. What's also important to understand is that the interface at which this change is happening, it's really, really small. So the discontinuity appears at the scale of 10 to the power minus 6 meters, which is micrometers. The interface itself is even smaller, probably 0.1% of the thickness of the molecular mean free path. We're talking about some angstroms worth of length. And because of the few number of molecules in the interface, we cannot really measure what's happening at the interface. So we don't know what is the variation of temperature at the interface. So what we do essentially is that we try to extrapolate what's happening in the liquid layer and something in the vapor layer, and then we put them together at the interface and we say, okay, that's the discontinuity. So essentially, the ambiguity at the interface, coupled with the microscopic dynamics of the interface, contribute to this discontinuous modeling of this whole entropy change across the interface, which allows you to calculate flux, evaporation rate, and things like that. So a very important development. Objections could be that if we scale it down, it could still be. So a lot of people tell me that if we scale it down, it could happen that the discontinuity somehow disappears because temperature might still be continuous under the hood somehow in some way. The problem is that that's not really the case, and no matter what scale you look into, at least the scales that are possible within our scientific limits, every single scale shows discontinuity, and a huge discontinuity, including in simulations, including in theoretical predictions, including in experiments. And also because the whole idea of there being a local thermal equilibrium at the interface where something is evaporating very abruptly, it breaks down. And this is of the order of 3 angstroms or 4 angstroms probably. Oops, that was very quick. I'm sorry about that. Let me go back. There was a little glitch in the, yeah. And as I mentioned, this is also a theoretical prediction of the KTG and the Boltzmann transport equations. You might also say, why are the microscopic results significant for macroscopic results? When we think about continuity, we often think of microscopic models at the bigger level, so at the level of classical objects. And at this level, we can still apply many of these continuum models. So why is this result significant? The problem, as I mentioned, is that it is not only present at the microscopic level, it also affects what is happening at the macroscopic level because of it being a part of the whole modeling process. It affects the dynamics of evaporation, it affects the bulk temperature jumps, it affects the rate of transport, the flux, and things like that. And no matter how you try to model this is another what we discussed in the paper in much more detail, so I can't go into because of the lack of time. No matter how you model this, you find that you have to model this as a discontinuity. If you want to get it right, it must be discontinuous. Otherwise, it just won't work. And it's not only the case that this is present only at the microscopic levels in evaporation and in phase transitions. Discontinuities have been recorded in many different kinds of strange spaces, including interstellar spaces and at sun's corona, where the denser parts of the sun are much colder than the dilute ones that are just above the sun's core. So there could be millions of degrees hotter. So there's a huge jump, there's a huge discontinuity in the solar atmosphere when you think about the core and its outer atmosphere. And this is very contrary to what somebody expects. And this is an open problem in astrophysics, and people are still looking into this. So just to make a point that discontinuities are important even at the microscopic level, and they are a topic of current research. Another objection could be, can we not just smooth this out? We have all kinds of mathematical functions that we can use to extrapolate something from the vapor and liquid bulk, and we can just erase this discontinuity and think of a nice continuous function across the interface. The problem is that the model that I discussed, and many models that model this change in entropy or evaporation flux across the interface, they are based on quantum mechanical discrete probabilities. So they model the movement of molecules based on what is the expected rate of transfer based on the laws of quantum mechanics. So you cannot have a mathematical function that can give you a continuous description, and it cannot be tried at the same time. So that's out of the cards. And as I mentioned earlier, that it's not that the discontinuity is somehow derived in some metaphysical sense, in the mathematical model. It's just that it's assumed as a starting premise. There are some models that use SRT, or the statistical rate theory, which uses quantum mechanics to model the situation, which use continuous profiles of temperature. For example, if you're studying absorption of a gas on a solid surface, sometimes it makes sense to use a continuous model. So it really depends on the context which you're looking at as to which kind of model is adequate to understanding what's happening on the ground. And another important thing is that when you do extrapolate something like this, a lot of these models also ignore many important factors at the microscopic level, which include, for example, convection currents. For example, if a droplet is evaporating, the surface tension that develops in the droplet at the microscopic level sometimes drives convection currents and drives heat into the vapor bulk. And that's also responsible for a lot of the molecules leaving the liquid surface. And that is completely left out in the continuum model. So all these important effects, which can give you a much better prediction of the evaporation rate across the interface, are being left out in the continuous description. So, and something similar happens when you think of solid-solid interfaces. But this one is a bit more nuanced, and the reason is that in the case of the liquid bulk and the gaseous bulk, we only have one kind of thermal carrier, which is being affected. When you think of two different solids where you have some kind of transfer of heat across an interface, you might have many different kinds of thermal carriers. For example, you can have electrons, you can have phonons, you can have magnons, and things like that, which are responsible to transmit heat and couple between each other and ensure that the system reaches an equilibrium after some time. But that is not always the case. So when you're modeling something, so let's say you're shining a laser on a surface and you want to study what is the rate of emission of electrons from a surface. And to know that, you need to know what is the temperature at the interface. And so models that are based on continuous descriptions would give you a wrong prediction because these models fail to take into account that many of these important thermal carriers, like electrons and phonons, do not necessarily reach equilibrium at the interface. And the reason is there are different vibrational profiles and different properties and things like that. So it might take them a long time to come to equilibrium, which is much beyond the measurement window. And in some cases, they might not even reach equilibrium, where you have a persistent discontinuity at the interface, which is not that uncommon. So essentially, and because the scale of the interface, as I mentioned earlier, is really, really small, you cannot use a description that involves just continuity because it erases all this important information at the microscopic level. And also because, as I mentioned earlier, the definition of temperature itself at the interface becomes a bit ambiguous because of, there being very few molecules, there being a really small scale where you can't really average out this quantity. In most descriptions of temperature changes in a system, what we tend to do is that we take a volume. We've tried to average things out. So all the microscopic vibrations are usually fully averaged out in a little volume. And that works in most cases. But in cases like this, like in case of evaporation of a liquid or the solid-solid interface, because the variation in the microscopic level is so much, no sampling volume will do justice to the whole averaging process. And so you will end up getting either very strange results or incorrect results, or you must model this discontinuously. I'll leave this for some of the time. This is a technical point. And this discontinuity has been, as I mentioned earlier, for the case of the liquid solid gas interface, it persists in simulation studies. So it's not just an experimental result or a theoretical prediction. It's been seen when you simulate the molecules and their movement. So when you simulate thermal carriers across the interface and how they behave and what is the rate of heat transfer. And in some cases, you also get very strange and very anomalous results. For example, estimates based on quantum mechanics, which use a certain distribution function for thermal carriers, which are a bit different from the ones that are used in classical Maxwellian distributions. They might give you very different temperature results, and they become equal really only in very high temperature ranges. And so these different estimates of temperature and the ambiguity at the interface, the difficulty in defining the temperature there, all the microscopic dynamics, they only make it evident that all these anomalous cases, call for study. They call for a deeper investigation of what's really happening and what kind of model we should use to study these systems. Let me address objections again, and then I'll conclude the presentation. One objection I got from a referee earlier, and I'm very thankful to him, is how do we even speak of discontinuities legitimately in cases where you can't even define that quantity, so it's not even well defined. One response is that it's a routine practice to show discontinuities and mathematical functions where they blow up at certain points, but they're not well defined. So it's not very strange that we model them discontinuously. I think the idea is not to take this seriously as some metaphysical discontinuity, because that's what people tend to do. And my larger point in this presentation is that they're both just ways of looking at a system. And both these different ways of looking at a system give you results based on what is relevant to that particular situation. Another question that the referee asked me was is every case of discontinuity simply a case where the temperature jump between one point and another is not well defined, or are there cases where there is a jump that is only happening at a very small distance? And as I mentioned earlier, to just reiterate the point, the answer is not so straightforward, and the reason is because of the complex dynamics of the microscopic level, and because of certain limits in our theory and experiments to measure temperature and measure jumps at really those small scales. So yeah, the answer is not so straightforward, and also because the temperature at the interface is very ambiguous. So just to reiterate the point, the ambiguity at the interface, which is seen as a very sharp jump, is then modeled as a discontinuity. But what's important, I think, with the larger point, the larger takeaway from this little talk is that both these representations work, and to me, at least to my mind, they seem to be idealized. In both the cases, you might think that a discontinuous representation is de-idealized and somehow it's closer to what's true. But in a case like this, where there's a lot of ambiguity about the dynamics of the microscope, because we don't understand it, it's not so clear, and because it's pretty is all developments in physics that are still taking time. Even a discontinuous representation seems to be idealized, and it seems to conceal what is happening in the system at a deeper level. To conclude the talk, I've argued that an abrupt change in the microscopic material conditions, in phase transitions at the liquid gas or vapor interfaces or solid interfaces, enters the thermal transport models as discontinuities. So this is anomalous, and it's been important to discovering important things in thermal physics, including the rate of evaporation, understanding of the phenomena in a better way. And the reason why these models of the continuum level fail is because the description can be strongly coupled with the macroscale material constitution and the thermodynamics that is happening at this small scale. So opposing Batterman and Butterfield and other people, continuum idealizations are not indispensable in principle. They are dispensable, both explanatorily, empirically, and pragmatically. And it depends on the context which we look at, where these models tend to work on or tend to fail. And sometimes they give you a lot more valuable insights into what is happening in a physical system than that can come forth from this simplistic continuum profile, which then makes you believe in all sorts of things, including structuralism, including continuity and abstraction and things like that. And therefore, temperature is not, this is a scientific contribution of the paper, is that temperature is not necessarily a continuously defined function. Its continuity, when applicable, is contingent upon various microphysical factors. This is a bit of a glitch in the talk. And the final question that I want to ask is due to 2 points. The first point is, so there's this idea that mathematics kind of maps the world, or at least we have a way in which we can abstract from the world. We find a model to fit in the world somehow. We kind of wrestle mathematics in the world the way that Bruno and French like to use in their book, amazing book. And then the idea is that should discontinuous representations only work when they somehow reflect nature that is also fundamentally discontinuous? Or are these representations similar to continuous representations also just idealized of something that and hiding something that's much more complicated underneath? Or put alternatively, presuming that both of these representations are idealized, let's assume that for a moment. Is this whole mathematical dichotomy that the world must be continuous or it must be discontinuous, because that kind of completes all the possibilities, is it enough to understand the world? Is it enough to tell us what the world is like? Is it enough to account for all the complexities of the world? And I'll leave you this question, which I've been struggling for quite some time, and I hope to find an answer with the discussion, or probably a hint to the answer. And I thank you for inviting me, for having this in this talk. And I look forward to your questions and your comments. These are the references for the talk that you can have a look. And in case you have a question, you can always ask me. Feel free. Thank you very much.